Hello, my name is Viren Mandaogane. This is the first talk in our 7-day Astronomy Week organized by Astro Club FC. In this world, everyone has a story to tell. But today, we are going to hear and understand the birth story of our universe, which is the Big Bang. I want you to observe this tick and talk that is happening at a periodic time. Well, such kind of a clock is continuously present in our universe. Time is passing by and there is no stopping to it. However, our story is going to be about the beginning of the universe. So, what does actually beginning mean? Basically, what we are going to do is we are just going to focus our entire attention to what we call as the first tick. That is at t equal to 0, or rather the entire journey our universe took to reach towards the first tick. Now I'm going to introduce to you the timeline ruler. This gigantic number is going to be used as a scale of measuring time. This is going to be used as a reference throughout the video, and it is important to know what this actually means. This ruler is the time scale of the universe that spans nearly 62 digits, from very smallest possible time, the Planck time as it is called, to the very longest time, that is the age of our universe itself. The confidence that there exists such a story is based on our knowledge of elementary particles. Physics that is understood today stands on first Albert Einstein, who gave us the general and special theory of relativity, which actually tells us how matter moves along in space, or I must correct myself to say, how space tells matter how to move. On the other hand is Niels Bohr, who gave us the fundamentals of the major theories of quantum mechanics. This is how the microscopic world works. These together form the pillars of the 21st century physics. However, these two pillars don't go well together. To understand our story in a better way, we are going to divide the story into three eras. That is, the era of quantum gravity, the era of inflation, and the era of Big Bang. This era of Big Bang is basically on the topic where we are going to focus more. First, the era of quantum gravity. These were very uncertain times that spans 1 billionth of our tick. Today we know that there are fundamental forces that exist in nature. Namely, there are four: the strong nuclear force, the weak nuclear force, electromagnetic force, and gravity. However, during this time, all these forces did not exist at all, let alone forces. The entire physics as we know today does not follow during this era. All the physical and mathematical tools that we have developed till now are not applicable to this era. Next is the era of inflation. Less certain is also the era of inflation, beginning 1 billionth of a tick after t equal to 0 and ending at about the 1 tick. This period is of hyper rapid expansion, although there is a theoretical framework for understanding it, the details are still in flux. And now we come to the most important part, that is the era of Big Bang. We will see a story of the take, as we call it, in detail as it enters into the era of Big Bang, which approximately is over here. So this is where our story begins, the era of Big Bang. The name Big Bang is something of a misnomer. It was coined by the British astronomer Fred Hoyle, who espoused a competing theory in which the universe existed forever with no beginning and no end. Well, if that was the case, we wouldn't have this story today. Big Bang seems like an explosion of persisting space, but it is important to understand that matter did not explode into space. Space itself expanded and carried everything with it. The era of Big Bang begins at the end of inflation and continues to the present day. Now, we quickly move past a great amount of zeros in our timeline, during which our universe expands and cools. What I really mean by cools is that if we consider that this is our t equal to 0, I'm sorry, is that if this is our t is equal to 0, then from here till over here, the kinetic energy goes on decreasing. That is meaning of the cool, the temperature itself goes on decreasing, and therefore the kinetic energy of particles in the universe goes on decreasing. At these stages, what happens is the quarks stick together to form protons and neutrons. We all know that the atom is made up of proton having positive charge, neutron and electron, each having a positive, 0 and negative charge. However, these two are considered to be nucleons, which are further made up of quarks that are arranged in a specific manner which give them their charge. Let us see how this is possible with an example. So, we have two examples over here in which these are two atoms that are formed by when three quarks were stuck together. Well, as you see, that these quarks have a property of charge. Now let's try adding this. Plus 2 by 3 plus 2 by 3 and minus 1 by 3. What does it give us? Is positive 1. Therefore, this is our proton. Whereas over here, 3 would give us 0. And therefore, this is neutron. So, what I meant was by cool as such actually meant 10 million degrees. But this temperature, however, was stable enough for these quarks to stick together to form protons, to form neutrons, which participate in the strong force. Well, I must warn you now, as we are now going to take a very dramatic and a confusing turn. This is when finally we are at t equal to 1 second in our timeline. This is when the temperature is merely 10 billion degrees. This is too cold for new particles to form. So what I mean by producing new particles and antiparticles is that suppose I have two protons. Now what they do is, if this proton is going over here and they meet each other like this, what happens is the two protons, let me use a different color, the two protons however exit. But there is something else that happens too. What happens is the kinetic energy of these two protons when they collide converts into a neutron and an antineutron. Roughly during this time, matter and antimatter were present at an equal amount, when suddenly something drastic happened and all the antimatter that we knew vanished. Now it is high time that we got a general introduction as to what antimatter actually means. Well, in nature, for every yin there is a yang. That is, for each particle of matter there is a corresponding type of antimatter, an antiparticle. An antiparticle has the same mass as its particle partner, but all its corresponding characteristics are opposite to that of its partner. For example, if we take an anti-electron has the same mass as an electron, but its electric charge is +1, whereas electron's electric charge is -1. Like electrons, all particles that have an electric charge have an antiparticle partner that have opposite electric charge, making particle and antiparticle distinctly different. If a particle and its antiparticle would combine, they annihilate, they totally destroy one another and leave behind only energy. This can be explained by what is called as a Feynman diagram. That is, suppose I have an electron and I have an anti-electron, or rather it is called as a positron. So what happens is, when these two meet up, they completely annihilate each other. That is, when they meet at the center over here, the energy that is carried out is carried through two photons like this. Roughly during this time, as I said, matter and antimatter were present in equal amounts. That is, the yin and yang were followed. This is called as the CP symmetry. That is, nature does not favor between a particle and an antiparticle. But during our time, that is at t equal to 1 second, the weak nuclear force, however, becomes biased towards matter, and thus the CP symmetry breaks and matter has an upper hand. Antimatter, however, ran out before the matter did, and today there is no antimatter left in the universe. Everything we see is made up of the slight excess of matter. Well, can you guess by what amount did matter exceed antimatter during this period? Let's suppose that the amount of antimatter was 1 billion. How much do you think that the matter exceeded from here? Well, the amount of matter was 1 billion and 1 only. Such was the slight amount of matter which was enough for the antimatter, or rather the CP symmetry, to break completely. And thus antimatter vanished, and all we know, all the matter that we know today is just this excess amount of matter that was left. Well, now after the dramatic story of our antimatter, we will now move forward in our timeline. This is where there is synthesis of light nuclei. This is at t equal to 100 seconds, when the temperature is now nearly 1 billion degrees. This is where our familiar atoms, that is, the deuterium, the helium, and lithium in very small amounts, but lithium start to hover around, roam around our early universe. Well, before we move ahead in our story, we will have a quick recap as to what all has happened till now. So, first, we saw the very uncertain era of quantum gravity, where none of the physical laws actually made sense. Then, we moved ahead to the era of rapid expansion. This is called as the era of inflation. Then, what we focused our attention to was the era of Big Bang, during which we saw that first protons and neutrons came into existence. Then we saw that there was the antimatter vanishing story. After that, we saw that the lighter nuclei came into existence. Okay, so far so good. Now we move on to t equal to 3,80,000 years. This is where the first atoms formed. The temperature now has dropped drastically to 3000 Kelvin. This favored the formation of okay, I'm sorry. Oh, what is this? Well, this was not a glitch, and I think you understood that. Well, as you see, I thought it was high time I told you something important that came out from this particular time period to us. That is, I have been telling you this story about the birth of our universe without giving you any proof of its existence. I mean, why would you believe that such a story exists in the first place and you're utilizing your time to listen to this story? Well, this is not philosophy and you must demand proof. So, if I ask you that if someone comes to you and says that give me the proof that you were a child once, what would you do? Well, we would show them our birth certificate and stuff. But what would we really do is we show them a time in which we were actually babies, or rather in our growing years. That is, we show them our childhood photos. Well, some of them won't even believe that you look that way. But that is a different thing. This over here is somewhat, or actually, this is a childhood photo of our universe. That is, this is called as the cosmic microwave background radiation. This picture is when the universe was nearly 13.7 billion years younger. This cosmic microwave background radiation was found by Ralph Alpher, Hans Bethe, and George Gamow in 1948. Well, there's a joke that in their paper, when they published the paper, they arranged their letters in specifically this pattern so as to represent the Greek alphabets of alpha, beta, and gamma. Well, such is the humor of physicists. But rather than telling you about how this proof came into existence or how it was found, which is an entirely different story of its own, I would rather tell you why this proof is important, or else what it actually means to be the proof of the birth of our universe. So, this graph is the energy distribution of the cosmic microwave background. This is said to be the most perfect thermal spectrum ever measured. Planck suggested, Planck solved the ultraviolet catastrophe by suggesting that radiation from hot object is quantized. That is, it comes out in the fact that somewhat like this. Planck also showed that intensity of radiation at each frequency has a very well defined shape. This is called as the Planck body spectrum. The CMB, however, conforms to Planck's prediction to within an observational precision of 1%. Well, now you would say, how is this even proof? You were just telling that the model accepted to Planck's radiation. Well, if we move ahead, another remarkable characteristic of cosmic microwave background is its uniformity across the entire sky. The difference in cosmic microwave background temperature between any two regions of the sky is no more than 1 part in 100,000. Well, if we adjust Earth's motion accordingly. But how is this possible? You see, Normally, objects come to same temperature by sharing heat through contact or radiation. Like in this picture, hotter objects transfer heat to colder ones until they equalize. But how can this happen in a vast universe? Well, how can a region 13 billion light years at north of Earth have so nearly the same temperature as the region that is 13 billion light years south of Earth? If you really understand the matter, it would take at least 26 billion years 26 billion years for these two regions to send energy to one another. But we know that the universe is not that old. Well, then what would be the explanation? Did thermodynamics fail? Well, no. Thermodynamics can never fail as a theory. The only explanation for this temperature uniformity is that our entire universe was once completely contained in a very small volume, making it easy for all its parts to share the heat evenly. Before the discovery of Big Bang, many physicists had opposed the theory of Big Bang. When the CMB was discovered, they struggled to find alternative explanations for its origin. But however, everyone failed. Only Big Bang theory is able to explain the cosmic microwave background radiation. And thus CMB provides the strongest evidence for the Big Bang theory. So before we proceed further with our story, I would like to tell you that why did we deal with the cosmic microwave background, as in why did we deal with the evidence of the story itself at that particular side of the first atoms. It is important to note that this is because the time when these first atoms were formed, these atoms were neutral. That is, the CMB photons that came out from the during this era, that is 13.7 billion years ago, did not have any interaction with the atoms during that time. That is, the universe had become transparent. The universe was no longer filled with unpaired charged particles that absorb light. So, we come out to the first stars. This happens at t equal to 200 million years. The first stars form. Because the universe's density is still very high, the first stars are particularly very massive and short-lived. This is the time when the universe had these tiny lightning bulbs all around it. However, from these stars, the core of these stars produced heavy elements, namely carbon, iron, and oxygen. So now, as we move on to our present day, we see that at t equal to 9 billion years, our solar system forms. Then, the Sun and the 8 planets are formed roughly at the same time. At t equal to 10 billion years, that is 3.46 billion years ago, first signs of life have been found on Earth. These are stromatolites. They are layered deposits believed to have organic origin. The oldest stromatolite is estimated to be 3.46 billion years old. And after that, we know evolution happened the way it did. And thus we are here, in front of our computer screens. Although we must celebrate the fact that as we have entered the present, we will now become the part of the story that we were hearing till now and trying to understand. This picture by NASA gives us a brief overview of our entire story and gives us the possible theories that might happen ahead. In this video, most of the concepts that you heard would be discussed in our further talks as the Astronomy Week proceeds. Our basic goal is to try to make these cutting edge concepts as accessible as possible. We are trying to convert physics to English, equations to graphics, and rather the tough concepts into vivid images that you and me can understand in a better way. But obviously, the science is not going to be dumbed down. This is real science. Real science for people like you and me. And thus, there is going to be a lot to think on. That is what I can promise. Hello. If you like the video, please like, share and subscribe for further more videos and talks that are going to come up in this Astronomy Week. Thank you so much for watching.